My name is Catherine Deverin, and this is Lab 1. The purpose of this experiment was to calculate the amount of excess or deficient charge on U-tapes after an interaction. We could visualize how charged species react and understand how forces act on charged species. The fundamental principles involved are Newton's second and third laws dealing with force and Coulomb's law dealing with charge. As a result, I found that the U-tape was positively charged, and I calculated the magnitude of deficient charge on the tape, the number of deficient electrons on the tape, and the ratio of deficient electrons to atoms on the tape. When observing the interactions of U-tapes, I found that U-tape 1 and U-tape 2 repelled each other, telling me that they are both the same sign charge. Additionally, the U-tape was attracted to a negatively charged pen, which signifies that the U-tape is positively charged. Therefore, both U-tapes are positively charged as they repelled each other. I took some measurements to help out with the calculations in this experiment, including the length of each U-tape, the mass of each U-tape, and the distance at which the U-tape began to flow, which is shown through the diagram at the right. I assume that the charged tape is treated as a point charge and that all charge is concentrated at the center of the tape. Additionally, each U-tape has the same net charge. As shown through the free body diagram, the two forces acting on tape B were the electric force of tape A and the gravitational force. We know the equations for both of these forces, as shown on the screen, and because the net force in the system is 0 newtons with the system in equilibrium, the gravitational and forces are equal to each other, just in opposite direction. Therefore, we can set the two equations for these forces equal to each other, as shown at the bottom of the screen. To calculate the charge on the U-tape, we could apply the equations representing the equality of gravitational electric force that we showed on the prior page and plug in the measurements that I found for the system setup. Isolating and solving for Q provides an answer of 2.0 times 10 to the negative 8 coulombs as a calculated magnitude of charge on the tape. Next, to calculate the excess or deficient electrons on the tape, we know the charge of the tape as well as the normal charge of an electron. Therefore, dividing the charge of the tape over the normal charge of electron gives us the number of deficient electrons as 1.3 times 10 to the 11 electrons. The final calculation involved solving for the fraction of atoms that gave up electrons, which is shown through the number of deficient electrons over the total atoms of the tape, assuming that the charges and atoms are equally spaced on the tape. The total atoms on the tape can be found by dividing the area over the cross-sectional area of an atom. With this value of 6.5 times 10 to the 16 atoms on the tape, we can divide from the number of deficient electrons to get 2.0 times 10 to the negative 6 electrons to 1 atom on surface as the ratio. Next, I created a computational model to help visualize this experiment with spheres representing tape A and tape B and vectors representing the electric and gravitational forces from tape A acting on tape B. The code I used is as shown, where I first listed all the constants I would need and then wrote down the two equations for F gravity and F electric, as shown under the forces section. I then plotted the positions of both tapes as spheres with a distance between them at which B starts to float, as shown under Objects with tape A and tape B. Next, the goal of the code was to find the magnitude of charge on one piece of the tape, so I isolated Q in the equation, calculating the electric field, and printed this value, as shown under Calculations. The vectors representing both the electric and gravitational forces are shown under the last object section, originating from tape A and acting on tape B, with Y components corresponding to force. These were represented through two arrows. In conclusion, if electrons had positive charge and protons had negative charge, the observations would remain the same, because the basic rules of charge interaction would still apply. Like charges repel and opposite charges attract. If their signs were switched, protons and electrons would still have equal and opposite charges. It is important to handle the charged tapes as little as possible because our hands and other objects start out as neutral objects, so the positively charged tape would attract the electrons in this object, becoming exposed to a source that it would use to make its own system at equilibrium.